So in this lecture, we're going to be looking at what atoms are made up of and how scientists discovered that atoms weren't just indivisible particles that had no smaller units, but actually there were a number of subatomic particles that help define a lot of the characteristics and even identity of an atom or of an element. The first of these major experiments was in the late 1800s by J.J. Thomson, and he made a glass tube called a cathode ray tube, and basically applied a large, like high voltage between the anode and cathode. Now, this high voltage caused the cathode to emit this beam of particles. And you can see that in this yellow beam here called a cathode ray. And he passed this beam through two charged plates. One was positively charged and one was negatively charged. And what he found was that this beam was deflected away from the negative charge and towards the positive charge. And that meant whatever that beam was made up of had to have some sort of negative character to it because it was deflected away from negative. So, like charges repel, and it was deflected towards the positively charged plate, which, like, I'm sorry, opposite charges attract. And through further experimentation, he used magnets and was actually able to discover that whatever this charged particle was not only had negative character to it, but its mass was much less than that of an atom. And so from these experimentations, scientists were able to conclude a series of things about what was coming from these atoms that made up the cathode. Number one, these particles were deflected away from the negative plate and towards the positive plate. That was the observation. What does that mean? That means whatever was in the cathode ray contains negatively charged particles. Secondly, these negatively charged particles are much smaller in mass than an atom. And then thirdly, what he found was it didn't matter what metal he switched the cathode with. He could put different types of metals there. And regardless of that, these negatively charged particles that came from the cathode are the same mass, regardless of source. So every single atom that exists of every single element has to have the same exact negatively charged particles in it. And so they named these negatively charged subatomic particles electrons. That's the definition of an electron. It's a negatively charged subatomic particle with a mass more than 1,000 times less than that of an atom. So putting all those things together, scientists were able to deduce that there's something in an atom that's much, much smaller than an atom. It's got to have it's a negative, it's got to have negative character to it. It's negatively charged. Now I put a link in the notes here to see this cathode ray tube in action. So like a more modern version of this, and you can see firsthand how these negatively charged particles are deflected. Now, further experimentation was done by Robert Millikan, which he was able to show the actual properties of an electron. What is the actual charge and what is the mass? And he basically said, or was able to calculate, that the charge of an electron was negative 1.602 times 10 to the negative 19th coulombs. Coulombs is kind of the standard unit of a charge. Um, Now, we haven't talked about this scientific notation, like what does that times 10 to the negative 19th mean? You might have seen this in other math classes, but just to kind of show like how small this is, I'm going to write this number out here. And let's see, 1, 2, 3, 4, 5, 6, 10, 11, 12, 13, 14, 15, 16, 17, 18. 1, 2, 4, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18. And then there. So I think I did that right. 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Yep. There we go. So that's the charge of an electron. Now we'll talk about scientific notation in a little bit in a few chapters, but just to kind of demonstrate how small of a charge that is. And then its mass was 9.107 times 10 to the negative 31st kilograms. Now, I'm not going to bother to write that out, but that is even a much, much, much smaller value. So the mass of an electron is, that's small. Compared to an atom, that's over 1,000 times less than what a single atom would weigh. Now, scientists were able to confirm and document the properties of electrons, but positively charged particles were more elusive. They knew they had to exist because if there's negative things in an atom, there has to be positive things that balance that out because atoms, when they're neutral, they have to have an equal number of negative charges and positive charges. So there were a couple early models of an atom. One of the first models was they called it the plum pudding model or plum, not pudding, but plum bread pastry model, which basically was like, think of these electrons as little pieces of plum or like chocolate chips in a chocolate chip cookie. And they were kind of embedded in this positively charged dough, so to speak. Another model is that, well, no, the negative things, the electrons, are kind of orbiting a planet of positively charged matter, much like Saturn, the rings around Saturn. Um, Regardless of these, and there's debate back and forth what was what was the correct description. One thing I want to point out, which was later disproved, is that both of these models contain a significant volume of positively charged stuff. I know that word is a technical, it's not very technical, but that there was a large volume of whatever this positively charged things were. Now, it wasn't really till a little bit later where this positively charged stuff was actually discovered. And it was discovered by the physicist Ernest Rutherford, basically experimented with firing high-speed, positively charged alpha particles. We'll talk about what those particles are much later when we talk about nuclear chemistry and radioactive chemistry. Um, but he shot these very small, positively charged alpha particles through a thin piece of gold foil. And here what was really interesting about this is that most of the particles pass straight through the foil. And this barrier here is like a luminescent screen. So wherever an alpha particle hit the screen, it would like light up. And most of them just went straight through the foil. Now keep that in mind. Like, how does that happen? If these models here um, had to have like really dense, high volume amount of positive particles, how do most of these alpha particles get through? So keep that in mind. What he also found was that a few of these alpha particles got deflected, kind of like the cathode ray tube experiment, where negative particles got deflected by a negatively charged substance. How are these alpha particles, which are positively charged, being deflected? Well, the way they get deflected is if there must be something positive inside of this gold foil. And what was even more strange was that a very small amount of these particles got deflected almost back towards the source. And the only way that that happens is if those alpha particles are hitting something positive in the gold foil and being reflected backwards. So this is kind of an in-depth picture of Rutherford's experiment, where most of these alpha particles are going through the gold foil. Now, the way that that happens, if most of them go through, that means an atom has to have a bunch of empty space. So I'm going to go back up again. That doesn't fit either of these models. There's not a lot of empty space of positively charged matter. Like there's a lot of stuff there. So those two models don't fit Rutherford's experimental results. Now, how do we get the slightly deflected particles? Well, these alpha particles must be getting close to something that is positive, that has a much smaller volume than what scientists thought before. And so they're deflected slightly. So that's how we kind of get the small deflections. Now, how do we get these alpha particles reflecting almost like back to the source? Well, maybe they're actually coming in contact with that very small positive region inside of the atom. So Rutherford's experiments led to three conclusions about what makes up the space of an atom. Number one, since most alpha particles went through, an atom must be mostly empty space. Number two, since the alpha particles are positively charged, then they must be encountering something else positive in order to be deflected. And then number three, since a few alpha particles were, I'll say reflected, not deflected, but reflected backwards, there must be a small concentrated positively charged area at the center of each atom. And that small positively charged area, scientists now call a nucleus. So finally, we have a pretty good picture, or it's not complete yet. We'll see why in a second, but a somewhat complete picture of what the true model of an atom should look like. And I'm not going to draw pictures of it yet because we're going to see later on how um, these models get adjusted. So right now, our description is that electrons, which are negatively charged, surround the nucleus, which is positively charged, and the nucleus contains protons. And that was the name they gave to these particles inside the nucleus, these positively charged things. So a proton is simply the definition is a positively charged subatomic particle. And then secondly, a neutral atom must have an equal number of electrons and protons. Because if the number of negative things equal the number of positive things, then that makes something have a neutral charge or zero charge. Now, despite all this work and all this advancement, like knowing there's negative things in an atom, there's positive things in an atom, there was still something missing. And scientists knew there had to be something else. Because if they added up the mass of all the electrons and they added up the mass of all the protons, it still did not add up to the total atomic mass of the atom. So after some more experimentation, scientists found that inside the nucleus, there were also subatomic particles called neutrons. Neutrons are neutral, and I would circle, highlight, star that, uncharged, or that's what, neutral means. So neutral subatomic particles also found in the nucleus with a mass approximately equal to protons. So neutrons and protons have approximately the same mass, but neutrons do not have a charge. So the kind of big picture that we're putting in here is that, and I'm just going to use abbreviations, protons and neutrons are in the nucleus, and electrons are outside the nucleus. Now, the presence of neutrons helped scientists explain earlier discoveries where they found that atoms of the same element could have different masses. And these things were known as isotopes. So each of these three subatomic particles give an atom a certain characteristic. First of all, the number of protons defines the element. What makes one element different from the other is how many protons it has. So you'll never find, say, a carbon atom with the same number of protons as oxygen. So all atoms of the same element have the same number of protons. The number of neutrons defines the mass of an atom. And I'll highlight this now, and then we're going to kind of come back to it a lot in our next lecture. For example, let's take the element carbon. Most of the carbon that exists, we call it carbon 12. There's a very small amount of carbon that's called carbon 13. And the difference between carbon 12 and carbon 13 is one neutron. And then finally, the number of electrons in an atom defines its charge. Now, we'll talk about this much later down the road, but it is possible for an atom to be positively charged or negatively charged if it has more or less electrons than protons. We call those substances ions, and as I said, we'll talk more about that a little bit later. But it's important to note how um, each subatomic particle gives an atom a certain property or certain identity. Right, and that's where we'll stop with this lecture. We're going to kind of put a nice earmark on this when we come back and really dive a little bit deeper into subatomic particles and how we deal with these very small substances, these small subatomic um, particles.